now come to problem number 9. This is also a relativity problem, and it has to do with the topic of relative velocities, how velocities add up in reference frames in a relativistic point of view. So we have here a rocket going to the right. We're calling it rocket A. The person on top of the rocket is also shooting something with a speed of 0.7, the speed of light. The speed of the rocket is 0.9, the speed of light according to the Earth. Then you have a rocket B going to the left at 0.8 the speed of light, and then you have a person on rocket B. And then you have a reference frame C. So question says, A says, according to person C, which is this person, how fast are the two rockets approaching each other? B, according to person C, how fast is person A shooting the object? Okay. And then C, according to person B, how fast is person A shooting the object? Okay. So the basic relativistic velocity addition equation that we're going to use is velocity of A with respect to C is equal to velocity of A with respect to B plus velocity of B with respect to C over 1 plus velocity of A with respect to B, velocity of B with respect to C over C squared. Okay. Now, usually in the regular problems, we use this problem, but we ignore the bottom, because when you are going at non-relativistic velocities, these velocities are so negligible. When you multiply regular velocities, when you divide it by the speed of light squared, this is going to be almost 0. When you add 0 plus 1, you're going to get almost 1. So on Earth, most non-relativistic velocities, you just add them this way, right? So how would we do this problem if this problem was just regular speeds? Let's first quickly do it that way, and then we'll do relativistically, right? Going this way at 50 miles per hour, and another car going this way at 20 miles per hour, and then there was a person here on top of the car. They threw something at 10 miles per hour this way. Okay, so let's call this person A, person B, person C standing here. Question was, according to this person, how fast are they approaching each other? So what would be the answer to part A? Well, you would simply just do 50 plus 20, right? 50 plus 20, and you would get 70 miles per hour. And that would also be the answer if it was worded this way. According to car A, how fast is car B approaching it? It would be 70 miles per hour. According to car B, how fast is car A approaching it? That would be also 70 miles per hour. And then if you have a person watching them approach each other, how fast are they approaching each other? 70 miles per hour. So all those three questions are the same. Okay, question B, okay, was what? Question B was, according to this person, how fast is this person throwing their object? Okay, well, when we say he's throwing it at 10 miles per hour, what do we mean? Is 10 miles per hour with respect to the car that he is sitting on, right? So according to this person, how fast will that be going? It's going to be 50 plus 10, okay? Because 10 is with respect to the car, and the car with respect to the ground is 50. So you would do 50 plus 10, and you would get 60 miles per hour. Okay, you don't have to worry about relativistic effects when the velocities are that slow. Question C, according to person B, how fast is person A throwing their object? Well, according to person B, the car is approaching it with a speed of 70, right? So that already gives you a 70. On top of that, he's throwing it with respect to 10, with respect to the car, so 70 plus 10, right? So it would be 70, you add the speeds, and then you add 10 to it, and then you get 80 miles per hour. Okay, so for non-relativistic speeds, those would be the answers to the question. So how about this one here? A, so according to this person, how fast are they approaching each other? So it'll be 0.9c plus 0.8c over 1 plus 0.9c times 0.8c over c squared. Okay, you basically have to do sum of the speeds, and then you have to put the same speed here. Okay, So c squared, c and c cancel, and you end up getting 1.7c over 0.9 times 0.8 is 0.72, right? 72, 9 times 8, so 0.72. 1 plus 0.72, 1.72. So what is that? 0.988 speed of light. Okay? So that means that prevents anybody from seeing any other object going faster than the speed of light. And how fast will B think that A is approaching it? It will also be 0.988c. How fast will A think B is approaching it? It will also be 0.988c. Notice it's less than the speed of light. So nothing can even seem like it is going faster than the speed of light. Okay, so now let's answer question B. Question B is going to be what? Okay, so how fast? That would be like this one, 50 plus 10. So how fast will person C think that person A is throwing this object? Well, if you just simply added it, 0.9, 0.7, you would get 1.6. But again, you can't just add it. You have to do 0.9c plus 0.7c over 1 plus 0.9c, 0.7c over c squared. Okay, so similar as in that case, c cancel. You have 1.6c divided by 0.9, and 0.7 is 0.63, right? So you're going to do 1.6 divided by 8.2, the speed of light. Okay? Okay, now, last question. How fast will this person think that he is throwing? So what is the answer to that one? Well, remember, according to person B, how fast is person A approaching it? It's the answer to the first part, 0.988c. So person A is already approaching it at 0.988c, and on top of that, he's throwing something with a speed of 0.7c. So now we're going to add 0.988c to 0.7c. So we're going to do 0.988c plus 0.7c over 1 plus 0.988c, 0.7c over c squared, right? So because person B is already thinks that A is approaching it at 0.988, and on top of that you have to add the 0.7. Okay, so after that the calculation is very similar to that. C squared cancel, 8, the speed of light, 0.998. So that is actually larger. So that is getting very, very close, approaching the speed of light. It's larger than this and it's larger than that. Okay? So now you can see how to do all of these kinds of relativistic additions. Okay? If rocket B was headed this way, 0.8c, how would that change the answers? Okay? So you can see here, this one is overtaking this one, right? It's starting to do, it's going to start to approach it. So according to person B, how fast is person A approaching it? According to person A, how fast is person B approaching it? So they're going to be passing each other like this, right? So what would be the answer to the first part here? Well, basically all we have to change is we have to make this negative and we have to make this negative. Okay, so what becomes of the answer? 1 divided by 28, that becomes the answer changes quite a lot. If you didn't do the relativistic factor, it would give you only 0.1c. However, you have to now divide it by 0.28. This is going to be 0.0357. 0.0357c. Okay, how about this person? How will they think this person? Well, that won't change, 0.982. Okay, how about this person? What will they think this person is throwing it at? Right? How would that change that? Well, this person thinks that this is approaching it at 0.0357. 0.037c, right? And since this person is sitting on top of it, he's throwing the object in the same direction that he's traveling. That won't change either. So this will just remain 0.0357c plus 0.7c, and then you just change the bottom to 0.0357c. We could also change this one. We could say he's throwing the object backwards, 0.7c. So this one is headed to the right, he's throwing it to the left. What will change now? Well, the answer to the first question A will be 0.0357. How will this change? How fast will this person think this person is throwing it? So now you have 0.9c, 0.7c. Now you have to subtract, right? Like this. And of course here you're going to get 0.2c. And then here you're going to get 1 minus 0.63. Gives you what? 0.37. Of course, this answer will change. 0.2c minus divided by 0.37. And then how will this change? Well, here, since he's also on it, he's throwing it the opposite way. So you're going to have 0.0357c. And then since this is 0.7 is the other way, we're going to do minus here. And we're also going to do minus here, and then we'll have 0.7c. So the final answer will be what here, to the last part? Well, 0.0357 minus 0.7. On the top you have negative 0.6643c. And then on the bottom you have 1 minus 0.0357 times 0.7, you have 0.975, okay? So 0.6643 divided by 0.975, it gives you negative 0.681c, okay? So when I changed everything, basically, this guy was going to the right, this one was going to the right. It's going to be taking this over eventually, it'll catch up. But there's a person here throwing something to the left at 0.7c with respect to the rocket. So according to person B, this object going to the left will be going to the left at 0.681c. Instead of 0.7, it's a little bit slower, 0.681c, okay? So now you can see how to do all kinds of different varieties of these, okay? Thank you very much.